So how do we do it? The easy way to do this is to actually have two reference frames. So one frame would be our fixed or primary reference frame, and the second would be a rotating, also known as sometimes moving or secondary reference frame. So it turns out that when you use two reference frame, then the problem becomes a little bit simpler to solve. The analysis becomes simpler as well. So what we will do is we will attach a reference frame to the rotating rigid body on which sliding is happening or the relative motion is occurring. And we will of course have a fixed reference frame or a primary reference frame with respect to which we want to compute our velocity and acceleration. And the reason we want to compute our acceleration, especially with respect to a fixed or a primary reference frame, is because those are inertial reference frames. And if we want to plug in the acceleration expression or the values in Newton's second law, then we need to ensure that we are plugging in the acceleration which is measured with respect to an inertial reference frame. So we will have two reference frames, and we will see that by the use of two reference frame, our analysis actually becomes simple. So let's start with an object, and this could be a plate, okay, and there is a slot cut inside it, and I'm just cutting this slot and putting a pin inside here, but that is just to say that there is a relative motion, okay. So this problem is not restricted to just relating the velocity and acceleration between the 2 points where there is a slot and there is a rotating rigid body. The whole idea is that there is a rotating rigid body. On that rotating rigid body there is a relative motion occurring, okay. And let's call this point to be O, okay. So here we have a fixed reference frame. This is our fixed or primary reference frame. All right, let's call it O, capital X, capital Y. And then we have a rotating reference frame which is attached to this rotating rigid body. We'll call it small o, small x, and a small y, okay. So, I know this doesn't look really small, so I'm going to just make it a little bit smaller. Okay, it's a small o, x, y. So this is our rotating or secondary reference frame. All right. And what we are interested in is one, the velocity of the point P as measured with respect to the fixed reference frame, as well as its acceleration with respect to the fixed reference frame. All right. So we'll again start by showing the position vectors. So we have R of P, we have R of O, and then we have R of P with respect to O. So we can write, notice this is a small o plus R of P with respect to O, and that is equal to R of O plus, let's say this number is X from here to here and this number is Y, then this position vector R of P with respect to O in the rotating frame becomes Xi hat plus Yj hat. So I hat and j hat are the unit vectors along small x and small y, right? And if you want to write unit vectors along this, there would be maybe capital I and capital J, okay? All right, so once we have this, we can take the derivative. So this is R of P, and we will get velocity of P equals to velocity of O, okay, plus x dot I hat plus y dot j hat plus x d over dt of I hat plus y d over dt of j hat, right? So we get, let me write this again, plus x dot I hat plus y dot j hat. I will just repeat that, plus, let's look at this term. What is d over dt of I hat? So d over dt of I hat is nothing but the rate of change of I hat with respect to time. So the first question is there a change in I hat as time changes? Well, it turns out it does, because this rigid body is allowed to rotate with some angular velocity, right? Which means that I hat is also rotating because I hat is attached to this rigid body. So this is a moving reference frame, or also sometimes also known as body reference frame, because this reference frame is attached to this particular rotating body. So d over dt of I hat is actually not 0, even though its magnitude is constant, but its direction is changing. We have already seen how to compute the derivative of a unit vector. So if you recall from the very first chapter, we saw that d over dt of a unit vector is given as the rate at which it is rotating across the unit vector itself. So in this case, the rate of rotation is in the rotation is happening in the xy plane, which means that the axis of rotation is actually perpendicular to that, either positive z or negative z. So the magnitude part of that angular velocity is theta dot, and k hat indicates the direction, and we are taking the cross product with itself. So using that relationship, what we have here is theta dot k hat cross I hat, and d over dt of j hat accordingly will be theta dot k cross j hat. So let's substitute these derivatives in this equation. So we have x d over dt of I hat is theta dot k cross I plus y times theta dot k cross j. So this can be written as, I'm going to write this actually later on. So let me first write this, the last term. So this is theta dot k cross, I can associate x with I hat, and then I can associate y with j hat, and theta dot k outside plus x dot I hat plus y dot j hat. Okay. Now what is this quantity? This is nothing but the position vector of p with respect to O, right? So let's write that. So this would be VO plus theta dot k cross r of p with respect to O. What is this quantity? This quantity we will call V relative, for the reason that will become clear very soon. Okay, let me first finish writing this. And theta dot k hat is nothing but the angular velocity omega of this rigid body. So this is omega cross r of p with respect to O plus V relative. So that's the relative velocity relationship that we actually derive when we have a primary reference frame and a rotating reference frame. So these two terms over here will look familiar to you guys because you have seen them before. We had these two terms for translating reference frame as well, right? But there is an extra term over here which is V relative. So let's try to get some insight in what this V relative term really over is. So V relative is defined as x dot I hat plus y dot j hat. What is x dot I hat and y dot j hat? X dot is essentially nothing but the rate at which the x is changing in this rotating reference frame, and y dot is the rate at which y is changing in this rotating reference frame, because you still have the I hat and j hat. In other words, this is basically telling you the rate at which the point P is changing its distance from O, right? Because r, small r, is nothing but x I hat plus y j hat. So if P was moving away from O at a faster rate, then this relative velocity term would be higher. On the other hand, if P was actually fixed right over here and didn't move at all, so in other words, if this was a bug on our fan example, then this bug was not moving at all, then the distance between O and P would not be changing. In that case, this V relative term would be 0. And if this relative term becomes 0, then your equation reduces to the same equation that you had for the translating reference frame. So it turns out that this equation over here is far more general than the equation that you have for a translating reference frame. But it also tells you that you don't have to remember two equations to solve the problems. You can just keep this one in mind, okay? And you can see if the distance between the 2 points on a rotating rigid body doesn't change, then you can drop the V relative term. And this would reduce to the same equation that you had for the translating reference frame. Okay, so now let's talk about the acceleration, right? So how do we get the acceleration? To get the acceleration, we can continue to take the derivative of this equation, all right? So let's do that. So acceleration of P would be equal to acceleration of O plus omega dot plus omega cross d over dt of r of P with respect to O, which we know is xi hat plus yj hat plus d over dt of v relative. V relative is x dot I hat, so let me write that, x dot I hat plus y dot j hat. So this is acceleration of O. Omega dot is rate of change of angular velocity, which we call angular acceleration. So let's take the derivative of this. This is x dot I hat plus y dot j hat plus omega cross x I dot plus y j dot, and this we have seen before in the velocity analysis. This will be x double dot I hat plus y double dot j hat plus x dot d over dt of I hat plus y dot d over dt of j hat. So this is a long expression, but essentially all we are doing over here is taking the derivative of product of two functions, and in this case the derivative of I hat and derivative of j hat are not zero, so we also have to worry about them. So what do we have? We have acceleration of O plus alpha cross plus omega cross. Now what is this term? This term is v relative, we've seen this, so we'll write it v relative plus omega cross. This term we have seen, x derivative I hat plus y derivative of j hat, is nothing but omega cross r of p with respect to O. So let's write that. So that is omega cross r of p with respect to O plus, now let's get to the last two terms. This term over here, what is this? This is telling you the second derivative of x and the second derivative of y in the rotating or the moving reference frame, right? So just as x dot I hat plus y dot j hat over here was called relative velocity, this term over here would be called relative acceleration. So let's write that as relative acceleration, because this is the acceleration as measured in the rotating rigid body. Plus, what is this term? X dot d over dt of I hat plus y dot d over dt of j hat. So let's look at that. So I'm going to continue the next line. We get x dot d over dt of I hat is theta dot k cross I, because that's the rate at which I hat is changing, plus y dot theta dot k cross j. Okay, so what is this term? This can also be written as theta dot k cross x dot I hat plus y dot j hat. And now this is nothing but v relative. So this is equal to theta dot k cross v relative, which is same as omega cross v relative, right? So now let's combine all these terms. So remember, this is all this stuff over here is basically coming from this term right here. Okay, so the final equation is acceleration of p is equal to acceleration of O plus, I'm going to write this two cross product term first, just because this is the convention. Okay, so that's your third term right over here. Then we have omega cross v relative and omega cross v relative. There are two of these, so that would become 2 omega cross v relative plus we have finally one more term left, which is a relative. So let's write that. And that is our equation for relating acceleration of 2 points when you choose a primary and a moving reference frame, right? Now let's look at this equation, just as we looked at this equation over here for velocity in the box, and then now let's look at this one, right? And try to make sense of each term over here, what they might represent. So these two terms over here, we have already seen them before, right? And these two terms arise because there is angular velocity. So the rigid body is actually rotating, and that gives rise to an acceleration term. If you look at this term, this is because the angular velocity itself is changing in magnitude, and so that's the reason why you have this term. These two terms arise over here because there is a relative motion between the two rigid bodies, and that relative motion over here is between this point P and the rotating rigid body over here, right? So between P and O, there is a relative motion. Now that relative motion is reflected in relative velocity and relative acceleration. This term over here that you see is called Coriolis acceleration term. This term is called Coriolis acceleration term. This term over here is relative acceleration. That is because the relative velocity itself is changing.